Today we're going to be looking at section 6.2, which is on applying properties of rational exponents. And our goal is simply to do that, to simplify expressions involving rational exponents. Now we've looked at the property of exponents before, so we're going to use the same exact properties that we did at the beginning of chapter 5 here in chapter 6, only now our exponents are going to be rational numbers, which means essentially they're going to be fractions. So all of these properties, again, are the same. We're going to run through them again with rational exponents. So product of power says if we have the same base, we can simply add the exponents. So we're going to have 5 to the half times 5 to the 3 halves. Well, that's going to give us 1 half plus 3 halves is 4 halves. So that's 5 squared, which is 25. The power of a power says if we have a power raised to another power, we are going to multiply the exponents. So we have 2 to the 5 halves squared, so that's going to be 2 to the 10 halves, which is 2 to the 5th, which is 32. The power of a product says that if we have a product raised to a power, we're going to have to take that power through to everything inside. So we're going to have 36 to the 1 half times 9 to the 1 half. Well, 1 half is the square root. So we're actually going to have the square root of 36 is 6. Square root of 9 is 3. So 6 times 3 is 18. Negative exponents. Again, we cannot have a negative exponent. So if we do, we need to move it to make it positive. So 16 to the 1 half, or negative 1 half, will become 1 over 16 to the 1 half, which is the square root of 16. So that's going to be 1 over 4. The zero exponent rule means anything to the 0 power is simply 1. The quotient of powers, if we have the same base, then the ones in the numerator and ones in the denominator, we can subtract the exponents. So here we're going to have 4 to the 5 halves minus 1 half. Let's write my fractions in the same way here. So 4 to the 5 halves minus 1 half. So that's 4 halves, which is 2. So that is 16. And then the power of quotient is the same as the power of a product. That exponent on the outside needs to go through to everything in the inside. So we're going to have 27 to the 1/3 and 64 to the 1/3. Well, the third root of 27 is 3. The third root of 64 is 4. And so there is our answer for that one. So again, we're using the same properties that we did at the beginning of chapter 5, only now we're using them for rational exponents rather than exponents that are just integers. So let's go through a few of these examples in example 1. And again, we have to use the properties of rational exponents to simplify these expressions. So we have 12 to the 1/8 times 12 to the 5/6. So we are going to add those exponents. However, in this case, we don't have a common denominator, so we're going to need to get one. So we're going to make that common denominator 24. And so 1/8 is really 3/24. And 5/6, if we multiply both of those by 4, is really 20/24. So this problem, if we just simplify these, we're going to have 12 to the 23/24. If you look at the next one, we're going to take this 3 through to everything on the inside. So we have 5 to the first power times 7 to the 3/4 power. Same thing here. This is negative exponent, so we're going to move everything to the bottom. So it's going to be 1 over 2 to the 6th times 4 to the 6th raised to now the positive 1/6 power. And then we're going to take that through. So it's going to be 2 to the first and 4 to the first, which is 1 over 8. In D, we're going to subtract these two. Well, this is really a 5/5. So we want to have a common denominator again to subtract. So 5/5 minus 2/5 is 3/5. So this is going to be 10 to the 3/5. And in example here, we're going to take this 5 through to there. So it's going to be 56 to the 5/4 and 7 to the 5/4. And then if we look at this one, since they are the same, we can divide those. So this is really going to be 8 to the 5/4. Since they're both raised to the 5/4 power, basically they're going to be like terms, so we can take 58 divided by 6. So what we're going to do now is look at the example on page 421 in your book. And what they do is they give us a table, and they say that it says a mammal's surface area S in square centimeters can be approximated by the model S equals K M to the 2/3. So S is our surface area. M is the mass in grams and of the mammal, and K is the constant. Now in the table, in the book, they give you a value of K for some different animals, and they want us to approximate the surface area for a rabbit that has a mass of 3.4 kilograms, which is 3.4 times 10 to the 3rd grams. So they give us a constant for the rabbit of 9.75 from our table, and it's 3.4 times 10 to the 3rd, and then we have it to the 2/3 power. And so now we're just going to evaluate this. So if we go ahead and evaluate, we're going to have 9.75. We're going to just rewrite that. We're going to take 3.4 to the 2/3 times 10 to the 2/3, or 10 cubed to the 2/3, which is 10 squared. So we're going to have 9.75. 3.4 to the 2/3 is approximately 2.26 times 100. 10 squared is 100. And so this is going to be approximately 2,200. So the rabbit's surface area is about 2,200 centimeters squared. So there's the problem using rational exponents in your real life situation. So here are 4 guided practice questions for you to go ahead and simplify the answer. So go ahead and do questions 1 through 4. You can pause the video and then hit play when you are ready to resume. And here are the answers for the guided practice questions 1, 2, 3, and 4. Notice in number 4, we ended up with 4 to the 3/2. Well, we know that the square root of 4 is 2, and then 2 cubed is 8, so we can simplify that one down to a nice number. So we're going to jump down to the properties of radicals. And the properties of radicals are the same as they were when we did the square roots earlier. So if we have an nth root of a times b, we can split those up as the nth root of a times the nth root of b. So I can pull them apart. I can break them apart. The same thing is true for if we have a radicand, that is a fraction. If I have the nth root of a divided by b, I can break it up in the nth root of a over the nth root of b, provided that b is not 0, because that would give us 0 in the denominator. So in example 3, we're going to use our properties of radicals, and we're going to multiply these. So we're going to get the third root of 128 times 8. Well, that's going to give us 1,000. Well, the third root of 1,000 is 10, so there's our answer in this case. In B, we're going to go the fifth root of 96 divided by 3. Well, 96 divided by 3 is 32. And the fifth root of 32 is 2. So using the properties with some very basic radicals, and these are ones that work out really nice because, in fact, 1,000 had a third root and 32 had a fifth root. So in this case, we would get our answer down to a nice number. We're going to talk about simplest form. And again, simplest form is going to be the same as it was when we talked about just the square roots. Only again, now we're talking about radicals with index numbers n. Could be third roots, could be fourth roots, fifth roots. But here, it's in simplest form if the radicand has no perfect nth powers as factors, and any denominator has been rationalized. Again, you cannot have a radicand or a number inside your radical that has a root of whatever the index number is. So if we have a third root, you can't have a number, a radicand that has an 8, because the third root of 8 is 2. Or you can't have a radicand that's 27, because the third root of 27 is 3. So we're going to have to look at these just a little bit differently than we did at the square roots. And then again, we cannot ever, ever, ever have a radical in the denominator. So we're going to look in example 4 at how to simplify a couple of these. So in example 4, we have the third root of 104. So what we're going to do is this. We're going to break it apart. I need to find a number, a factor of 104 that has a third root. And if you're not sure how to do that, well, here's what I would suggest. Take your numbers, your smallest numbers, and cube them. So let's say 2. I take 2 cubed, and that's 8. So 8 is a third root, has a third root, and that's 2. Well, I'm going to check, is 8 a factor of 104? Well, in this case, it is. It's 8 times 13 gives me 104. And so now the third root of 8 is 2, and there's nothing I can do with the 13. 13 has no factors that have a third root, and so there is our answer. Now, if 8 would not have been a factor, I want to try the next number that is a perfect cube. And so that would be 3 cubed, which is 27. You would check, is 27 a factor? If that one doesn't work, check the next one, 4 cubed. 4 cubed is 64. So we want to keep trying numbers that are going to be factors like that. All right, and so what we're going to do next is we're going to look at this one. And there are a bunch of different ways to do this, but the simplest way is to always look at your radicand and see, is there another way that I can write 27? Well, in this case, I know that 27 is 3 cubed. 3 times 3 times 3 is 27. And our goal is to rationalize this denominator. So I'm going to write it like this, and the reason is like this. Remember, when we talked about square roots, and let's skip this problem for right now. We'll jump to something else. But let's say we had a problem like this. 4 times the square root of 3. Sorry, 4 divided by the square root of 3. If we rationalize this denominator, we had to multiply the top and the bottom by the square root of 3 over the square root of 3. Because that's going to get rid of our radical in the denominator. Square root of 3 times square root of 3 is 3. And then our answer was 4 square root of 3 over 3. The same thing is true in this problem. We have to figure out what are we going to multiply by to get rid of that in the denominator. Well, the reason I change it to 3 cubed is because I know if I find the 4th root of 3 to the 4th, those 4's in the index number and my power will cancel out. So I'm going to put this as 3 to the 1st. And so if I did that on the bottom, I have to do it on the top. And the reason is now I have the 4th root of 30 over the 4th root of 3 to the 4th. Well, if we notice here, these two 4's are going to end up canceling out because the 4th root of 3 to the 4th will be, well, that'll be, if we write that in rational exponent notation, that's 3 to the 4/4, which is 3 to the 1st. And so really, our answer for this problem now is the 4th root of 30 over 3. And we have to check two things. Is there a radical in the denominator? No, we got rid of that. Okay. 2, is there a radicand? The only radicand is 30. Is there a radicand that has a factor of this radicand that has a 4th root? Well, let's take 2. 2 to the 4th is 16. Is 16 a factor of 30? No. So let's try 3. 3 to the 4th is 81. 81 obviously is not a factor, so there's no way that we can reduce that any further. And there is our answer. The next thing we're going to talk about in this section is like radicals. And like radicals are radicals expressions with the same index and the same radicand. So if we notice in A, this is the 5th root of 12, and this one is the 5th root of 12. Those are exactly the same, so I can put those like terms together. Well, I have 7 of them minus 1 of them. So 7 minus 1 is 6, so I have 6 of those. The same thing is true with our next problem. I have 9 to the 2/3 and 9 to the 2/3. I have 4 of those in the first one and 8 of those in the second one. So that gives me 12 of them. Those are like terms. In the third one, they are not the same. I have the 3rd root of 81 and the 3rd root of 24. So what we're going to want to do is simplify these as far as we can. So I'm going to go the 3rd root of something times the 3rd root of something. So let's break apart the 81. Are there any 3rd roots factors of 81? And if we look at them, it is 27. The 3rd root of 27 is 3. So 20, and also 27 times 3 is there. So we have 3 times the 3rd root of 3. That's with the 81. Now let's take the second part. We're going to do the same thing here. Are there any factors of 24 that are 3rd roots? And that is also true of 8. And 8 times 3 is 24. So now the 3rd root of 8 is 2. And we have 3rd roots of 3. Now notice these are now the same. So I have 3 of those minus 2 of those, which gives me 1 3rd root of 3. And you don't need the 1 in there in the front if you don't want to, but that is our answer in that case. So I would like you to try the guided practice questions 6, 7, 8, and 9. So go ahead and pause the video and hit play when you are ready. And there are your answers to the guided practice questions 6, 7, 8, and 9. Now, if you look at question number 8, I had the fifth root of 4 right here. Well, I switched that to the fifth root of 2 squared. Okay. Just because it was going to be easier for me to do that. Now, if you didn't do that, you could have multiplied. You would have had the fifth root of 4. You would have multiplied the top and the bottom by the fifth root of 4 to the 4th. Because now that would have been the fifth root of 4 to the 5th, which would have been just 4. However, if you do that, you're going to get a much bigger number in the numerator, and then you'll have to reduce that down at the end. And in number 9, we had to take a factor of 40 that had a third root out so that we could get like terms and add those two together. So in example 6, now we're going to simplify expressions involving variables. Now, there's a couple of different ways to do this. One of the easier ways to do this is change them all into rational exponents. Now remember, we know that this index number is our denominator if we write it as a rational exponent. So if we do this, we're going to have 625 z to the 12th raised to the 1/4 power. Well, if you take that rational exponent through, then that would be 625 to the 1/4 and z to the 12 times 1/4. So this 625 to the 1/4 is going to be 5, and this will be z to the 3rd. So our answer would be 5z to the 3rd. Now, the other way to do this problem is just to leave them in radical form. And some of you will like that much better. And here's how you would do that. I'm going to take and I'm going to write 2 radicals. Okay? And I'm going to put everything in the first one that has a 4th root, and I'm going to leave everything in the last one that doesn't. Well, in this case, everything does have a 4th root, so we won't need this one. But if you look at that, the 4th root of 625 is going to end up being 5. And then notice we divide those exponents. 12 divided by the index number is going to give us our 3rd root there. So we'll do the same thing for 4b. So it's 32 to the 1/5. And then that's going to end up being 5 times 1/5, which is 1. And n is 30 times 1/5, which is 6. Well, the 5th root of 32 ends up being 2, mn to the 6th. Okay, and we can do this the same way for example C. Now, if you like radicals, that's great. Leave it in radicals. Sometimes it's much easier to see. But if you take this, you break it up as the 6th root of r to the 6th over the 6th root of s to the 18th. Well, that is going to end up giving us r over s to the 3rd. And for those of you who like it in rational exponents, which I think it's easier to see, we're going to have r to the 6th, s to the 18th, and we're going to raise it to the 1/6 power. Well, 6 times 1/6 is 1. 18 times 1/6 is 3. And so there's the same way of doing that problem using rational exponents. All right, so if we look at D, we're going to do our rules for exponents. Now, I notice I have a 56 and a 7, so I'm going to simplify those. I'm going to get 8 over 1. So this is going to give me 8. And then I'm going to subtract my exponents. I have a to the 1 over a to the 5, 6. Well, 1 is 6, 6. So that's going to give me 6, 6 minus 5, 6, which is a to the 1 6th. And I have b to the 3 fourths. There's no b's in the bottom. And I have c to the negative third in the bottom. Well, that's got to come to the numerator to become positive. And so there is the answer for D. So moving to example 7, we're going to write variable expressions in simplest form. Okay. So here's where we're going to come and we're going to break these things apart. So let's look at example 1, or A, 7A. And I'm going to leave these in radical form to start with. So I'm going to go break this part. I'm going to take anything with a third root out. All right, so the number 6 does not have a factor that's a third root, so that goes in my second one. X to the 4th. So essentially what I'm taking is anything, since our index number is 3, anything that's a multiple of 3. So that's going to be x to the 3rd, which gives me just an x left. And then y to the 9th, all of it comes out, because 9 is a multiple of 3. And z to the 12th, and so then I have a z squared in the last one. So the third root of x cubed is x. The third root of y to the 9th is y cubed. And the third root of z to the 12th is z to the 4th. And then we have the third root of 6xz squared left as our answer. Now let's say that I do that same equation, only I would use in rational exponents form. You could do the same thing. You could even just write this third root of 6xz squared in rational exponents if you wanted to. So let's look at the next one. I'm going to break down b into the 7th root of p to the 8th over the 7th root of q to the 5th. Well, notice here, I cannot have a radical in the denominator. So I need to switch that. So if I do, I'm going to have the 7th root of, I need this to be the 7th root of q to the 7th power. So I need q squared here. And the reason is because now q to the 2nd plus q to the 5th is q to the 7th. And so if I did that in the denominator, I also need to do it in the numerator. All right. So now if we look at this, p, I have p to the 7th root of p to the 8th. Well, that is really going to be p to the 8 sevenths, which is p to the 7 sevenths times p to the 1 7th. So I'm going to take a p out of there. And so this is really going to be p times the 7th root of, well, I have 1p left inside, and q squared over, and then we said this is just going to be q. And there is our answer for B. And then example 8, again, is adding and subtracting expressions involving variables. So we're using, instead of, it's just like the examples that we did before, only now we have variables in our radicand. So again, third root of u, third root of u, they are the same. So 18 minus 11 is 7. And then we have third roots of u. Okay, as simple as that in the first one. Same thing as in the next one. We have a to the 4th, b to the 2/3, a to the 4th, b to the 2/3. Well, we have 15 plus 8, so that's 23 of them. A to the 4th, b to the 2/3. Now, if we look at c, we notice that these are not the same. We have to try to make them the same. So what we're going to do is try to reduce anything that we can. So we're going to have 10, the 4th root of something times the 4th root of something. Pull out anything that we can. So let's say 5. Is there any factors of 5 that are a 4th root? No. Goes in the second one. How about s to the 7th? And that's yes. We can pull out an s to the 4th here. And that means I'll have an s cubed left in the second one. So if we try to simplify that one, that's what we end up with. And then this will be 10, and 4th root of s to the 4th is s. So now we have 4th root of 5s cubed. So that part is simplified. So let's look at the next one. So that's going to be minus s. And again, I'm going to break them up. 4th root of something and a 4th root of something. 80. Are there any factors of 80 that have a 4th root? And there is, and it's 16. And the s cubed can't pull out. So 16 and 5 we have. So 16 and 5 is 80. And then I have an s cubed left. And so now the 4th root of 16 is 2. So this is going to be minus 2s. And the 4th root of 5s cubed. And if we look at this now, those are the same. I have 10 s times 4th roots of 5s cubed minus 2 s times 4th roots of 5s cubed. So we have an answer of 8s 4th roots of 5s cubed. All right, so let's go ahead and try the guided practice questions on 10 through 13. Go ahead and pause the video and you can hit play when you are ready to resume. And here are the answers for the guided practice questions on 10 through 13. Now, remember in this section, section 6.2, we talked about applying the properties of rational exponents. We need to make sure that we're comfortable looking at these problems either in rational exponents or in radical form and be able to convert back and forth. Sometimes it's going to be easier to use radical form. Sometimes it's going to be easier for you to use rational exponents. But we're evaluating these and simplifying these rational exponent equations and making sure that we look at, are they in simplest form? Okay, and two things when we look at them in radical form, we have to make sure that there's no radical in the denominator and there's no factors of the radicand that have a root of whatever that index number is. So here are your assignment sets for section 6.2.